All right, everyone. We've configured the RIP version 2 routing protocol. We did several things with RIP, and we'll do a lot more throughout the course. But now we're going to get into EIGRP. EIGRP. Yes, we are. Now, with EIGRP, there's a lot of things that we need to cover. It's a very important protocol. They want to call it a proprietary protocol because only Cisco, up to this point, was able to use it. I believe it was in 2011 or 2013, I don't quite recall, where they stated that it's now an open protocol where all vendors can use EIGRP. Do your research, find out. But for certification purposes, we're going to consider this as a proprietary protocol, routing protocol that only Cisco routers can use. All right. So what's so special about EIGRP? Well, first of all, it is a distance vector, but it's an advanced distance vector routing protocol. We'll get into it in a bit. It does use an algorithm like RIP uses Bellman-Ford. Well, EIGRP uses something called a dual algorithm, which stands for diffuse update algorithm for you abbreviation aficionados that you must know what everything means. Not that they're going to ask you in the certification, but at least you know it's dual. And it's a more intelligent algorithm. It does pay attention to a lot of things. There's a lot of other things that fall within that algorithm that it uses to calculate metrics. As you can see here, we have something here that is going to talk about, is going to use metrics as far as its calculations. All right. It also uses autonomous systems. All right. You can have up to 255 autonomous systems, but by default, it only has 100. Okay. And we'll elaborate a little bit further on in the presentation about autonomous systems. Now, it does have 3 tables that it creates. Obviously, every router creates a routing table. EIGRP also creates a topology table and a neighbor table. And throughout this presentation, we're going to go ahead and talk about those individually. And then comes to the issue of wildcard masking. And when we get there, we're going to take our little time in talking about that because this is a danger zone. I should have put like a little symbol there that says danger, all right? Especially for the CCNA. And you'll see what I mean when I get to that point. And then, of course, load balancing. This is something that EIGRP offers us. All routing protocols do. But with EIGRP, there's many things you can do to tweak, all right, to see which way your packets are going to flow, all right? Now, advanced distance vector routing protocol still uses hop counts. Just told you, set to 100, maximum is 255. Convergence time is much quicker than RIP, much quicker than OSPF. All right, now the first time that when it's trying to converge, okay, what it's going to do is it's going to send out a complete update to its neighbors. And then it just sends updates as needed. It maintains that neighbor relationship with its neighbor router using hellos. One thing to say about these hellos saying, hey, I'm still here, is the fact that they don't have to be the same. As with OSPF, the hellos must match. The hello intervals and the dead intervals in OSPF, they must match their neighbor router. In EIGRP, that's not the case. But that's how they maintain their neighbor relationship, their adjacency with their neighbor router. Okay? And that's exactly what I said here. And most importantly, the administrative distance of 90. Why do I stress the administrative distance so much? And I've talked about the administrative distance quite a bit. The reason being is, being an instructor, all right, when I give exams, right, to my students, I want to make sure that they understand the concepts. So I'll draw a diagram and I'll say, hey, if I configure these 3 routing protocols plus static routes, or let's just say 3 routing protocols, RIP, OSPF, and EIGRP, which out of these 3 will make it to the routing table? And I'll put all sorts of different answers that kind of make sense. But there's only one thing that's going to make that choice, and it's the administrative distance. Because the lower the number, the more believable the route. Now, it's an advanced systems vector routing protocol, yes, but it has link state qualities due to the fact that it has hellos, it creates tables, all right? It only sends updates as needed. Unlike RIP, where every 30 seconds or however you tweak it, you're going to get the entire routing table out on these updates. Now, I keep saying updates. I want to clarify that a little bit. When these updates are being sent, they're being sent via a multicast address. If it's RIP, it's 224.009. I got to do it or else I'll say too many zeros. 224.009. In the case of EIGRP, it's 224.0010. So when you see that, if you're to do a debug IP EIGRP and see what's happening in the background, and you may see a print screen that says, hey, 224 whatever, that's just an update. That's all it is. 224, that multicast address, is what's actually sending the updates of the routing protocol. All right. The dual algorithm. Now, when we get into dual algorithm, you see it says here we use K values and it calculates metrics. Now, the K values, and they're there right there. You can read them for yourself. All right. They must be the same on the routers. They must be the same on the routers. Meaning your bandwidth, your delay, your reliability, your load. And MTU is a toss-up, okay, because it all depends on the packets that you're sending back and forth. There's a debate if MTU really falls in there. But if asked, or you get to, pick A, B, C, D, E, F, G, or whatever the case may be, bandwidth and delay are the two main ones that EIGRP uses to make a decision to send the packet on its way. All right. So these K values got to match their neighbors. And this is how, or one of the things that the algorithm uses, all right, to create the best path possible. All right. So it calculates metrics, and you can see here is based on bandwidth and delay. All right. And one thing that it does, it generates a feasible and successor routes. Feasible successor and successor route. What does that mean? Now we'll talk about those also in a little bit more length. But basically what it is, the successor, right? I've successed. I'm the winner. So I will end up in the routing table. The feasible successor came in second place. So he's going to end up in the topology table. Now in the topology table, which we'll talk about in depth as well, all routes go in there. Every last known route will be in the topology table, but the feasible successors will always stay there. And we'll talk about that a little bit more later on. But the successor routes definitely will be in your routing table, and you do a show IP route and it'll be there. All right. And it's important that you want to have feasible successors because this, like it says right here, loop-free routes. EIGRP, again, quotes, guarantees a loop-free environment because of its calculations to create metrics. Even though it's based on hop counts, meaning you can only go as far as 255 routers, but it uses metrics. The lower the metric, the faster the route, and that's the way the packets are going to flow. So the design, if you decide to use EIGRP, is extremely important because you do not want to fall into routing loops because you can do it all on your own. EIGRP will say, oh, what's going on here? And then you'll have too many feasible successors, and that can create a problem, but that's beyond the scope of the CCNA. All right, so this is your dual algorithm. Remember your K values, please, because you will be asked this, I guarantee it. All right, and they're called K values, and there are your K values right there. Okay. Now, not much to say in the autonomous systems. Do you have from 1 to 65,535 autonomous system? What is an autonomous system? Basically, you're going to create, or they will create for you, and you may have to fix it, where all the routers must be in the same autonomous system, which means that they share the same routing table information. If we are all on EIGRP 120 and for whatever reason, one router we put EIGRP 12 because we forgot to put the 0, then that router will not participate with the rest of the routers because he's in a different autonomous system and he's not going to share his routing table information. Now, that's true for a single autonomous system, which the CCNA does. But there is something called route redistribution, where you can actually redistribute from one autonomous system to another. But again, beyond the scope, but just to let you know, because real world out there, you're not going to have the same autonomous system throughout different counties, throughout different states. You're going to have different ones, so you're going to do your redistribution. But again, it's beyond the scope. Just know that it can. So again, all routers must be in the same AS. All right. That's one of the things for the CCNA that you need to know. You need to be in the same autonomous system. All right. Keep that in mind. So when you look at a picture and you're doing EIGRP and somebody says, oh, this router's in 100, this one's in 200, this one's in 300, they're not talking. What's the problem? Oh, we're not in the same EIGRP autonomous system. Okay. All right. The topology table, very important. How do you look at that? Show IP EIGRP topology. And when we get into the lab, we'll go ahead and look at that. All right, there's a lot of things that we're going to learn in EIGRP. It is a complex protocol. There's a lot of things you can do with it, all right? And now for the new CCNA, there's a lot of things that they want you to do with it. Now, it maintains the following. All routes learned by EIGRP. I told you that. The feasible successor remains in the topology table. Why? It's a backup route. For whatever reason, the successor route, the best route, right? The active route goes down. It will query, EIGRP will query the topology table and then choose that route and put it in the routing table. That way it doesn't have to recalculate the whole thing. If you don't have feasible successors, then it's got to go out and send updates all throughout the routers to create this, new route to this network, and that just takes longer, takes up more bandwidth. So that's why the feasible successors are there. So when but again, you will have feasible successors. It all depends on your design. Okay. Now you got to understand, really, there's a bunch of codes in there, but there's two of them that I'm more concerned with. All right, which is passive and active. When you look, and you will see it, and you do a show IP EIGRP topology, on the left-hand side, you're going to see at the bottom, it says P, passive. However many networks you have or learned is going to have a P on there, which means passive. That means, hey, I've learned about this route. We have converged. It's okay. We're good. All right. If you see active, that means it's actively looking for that particular network, and that's an issue. Because a question could be posed like, hey, why can't you ping to this particular network? What's going on? And we're using EIGRP. You can do a show IP EIGRP topology. Take a look at it. It may say active. You may get a print screen. And all you got to do is just look. And the one with the active means it's still actively looking for it. It hasn't found it. For whatever the reason, that will be the issue right there. So you don't want anything to say active. You want everything to say passive. Okay? Now, what does FD or feasible distance mean? That is, the feasible distance is the best route to get to where you need to go. That's what feasible distance means. Now, we're going to do a little math. Don't go crazy, but we're going to do a little math later on how to create these feasible successors and what math it uses to say, hey, this is the metric and this is how I generated because of the feasible distance from this route to that route and all that. So we're going to get into that. All right, we're going to get into that a lot deeper, and we'll do little drawings and everything, and I'll show you how that math works. Okay? All right. The neighbor table, the name speaks for itself. Okay? It shows you who you're connected to directly. It shows you your neighbors. All right? It'll show you what interface it was learned on, what interface it's coming from. It's going to show you hold times. It's going to show you times that it elapsed. It's going to show you a bunch of things, but based on your neighbor. So another good command, show IP EIGRP neighbors, is good to see, hey, who's next to me? all right, sending me, and where is it coming from, this particular information. So the neighbor table, all right, the routing table, we know what that is. I mean, show IP route. We take a look. These are all the active routes. These are the routes that are going to take us to where we need to go. So if we don't see a route that we know that needs to be there, then that's an issue. Then we start troubleshooting. We start looking at the topology table. We start looking at our neighbors table. We start trying to do pings or trace routes or what have you. We start looking into other things so we can find out, hey, why isn't that particular route there? Well, we can always use default routes, can't we? Static default routes. Now, here's what I told you, wildcard masking, all right? It's important, all right? Wildcard masking is important. Let me slow down here. I didn't put my hand in my pocket. That means I'm getting serious, all right? It used to be where in the CCNA, you only had to configure it, like I'm going to show you, all right? Basic configuration is basically like RIP, only we're using an autonomous system, okay? Meaning you would put the class full address and you use an auto summary. You never used any wildcard mask. Can you use wildcard masking? Yes, you can. All right. If you don't use wildcard masking, it will go ahead and summarize it to the class full boundary. I saw, I'm going to say where, I saw an entire group of people take a certification and they were taught not wrong, okay, because you can configure wildcard masks in EIGRP, but not for the CCNA at that moment. So they all failed because it was a simulation. All right. I've looked at the books. They talk about wildcard masking. Are they going to put it in the certification? You got to read the question. Be ready. Because I'm going to show you both ways on how to do it. It's no big deal. But be very careful. Be very careful because EIGRP, you don't need a wildcard mask to configure it, but you can. All right, because usually the wildcard masking or configuring EIGRP with wildcard masking was left for the CCNP level, but now they're bringing a lot of things in. So be wary, okay, when you're configuring EIGRP, what is exactly that they're asking? Configure one way or configure the other. All right. My thought is they're going to stay true to the course and say, hey, this is the CCNA. Let's just have them configure it. They know it's a single autonomous system, class full boundary. Boom, you're done. Right? No auto summary. But we'll get into that anyway. Now, it does have load balancing. All routing protocols have load balancing, but we're going to look at it in EIGRP. Now, EIGRP has something called the variance command. And what the variance command does, you take a look at your metrics. Let's say you have a metric of 1 million on one, and you have a metric of 3 million or 2 million on another, and you want to bring those two together, okay, as one. Well, you will use a multiplier. So within the routing protocol, you would type in variance and then use a number, which is called a multiplier, and say, okay, what number can I multiply by one, the lowest metric, that would include the 2 million something, all right, in there? Well, you can put 3, okay, and it'll include between 1 to 2, definitely will be in there, 1 to 3, it will be in there. So that would include that, and then EIGRP will look at that and say, oh, okay, so I can go ahead and send part of my traffic this way and part of my traffic that way. So you can load balance across both paths. But you can also tweak it, right? You can go inside the interface and you can mess with the bandwidth, right? Or you can mess with the delay, all right? We're just going to mess with the bandwidth, and I'm going to show you first which way the packet's going to flow, and then we're going to make it go in the opposite direction by manipulating the bandwidth, okay? But that's EIGRP, and as we go through the labs, definitely we'll get a little bit deeper and explain a lot more on how EIGRP works. So I hope you're ready. I'll see you in the next one. Looks somewhat complex, doesn't it? But welcome back. No, it does not. This is the lab that we're going to be using throughout EIGRP, but I think I showed it to you already. If I didn't, there it is. Okay. And you see we have redundancy, not full redundancy, but we have redundancy because we could have thrown cables down this way, down that way, but the bean counters won't let us do that. All right, so but we have enough to create what we need to create. And even though you see it so complex, because we will be doing certain things like load balancing and tweaking and stuff like that, we're just going to do right now, when we get inside this particular lab, we're just going to do the very basics. The IP addresses are already there. By this point, you should know how to put an IP address on the interface, whether it be a serial or a fast Ethernet. Put the clock rate, turn it on. So you should be okay with that. You can see here the networks, but I want you to notice that they're all 10s. Everything's a 10. We're in the class A. All right. So, enough said. Let's get inside the lab and get this done. See you there. All right, everybody, here we are inside the EIGRP lab. Yes, I know it says basic, but we're going to use this lab over and over again for the advanced configurations as well. But what we're going to do is just basic configuration, all right, of the actual routing protocol. So over here, you can see we have all 10 networks, right? We have a set of 30 for each one because they're all point to point. So let's go to router 0, which is this router right here. We got 0, 1, 2, 3, 4, 5, 6. All right. But we have another network. You see other networks in between. All right. So let's go ahead and configure EIGRP. Remember, it is an advanced distance vector routing protocol. So we go router, EIGRP, and the autonomous system that we want, which is 120. We go network, not classful, distance vector, even though it's advanced distance vector, 10.0.0.0. Okay. And then we do no auto hyphen summary. Control Z, WR, which you know you guys can do on the test. All right. So let's go ahead and pick router 1. Yes, I have them all open already for you. But let's make life easy for us. Router, EIGRP, 120, network, 10.0.0.0, because it'll summarize it. It does summarize just like RIP version 2. No auto hyphen summary. Then we'll do a WR. Then a couple enters there. We'll do Control A, Control C. And then all we got to do, let's get rid of that notepad right there. Go to config T, conf T, paste. Then we go to the next router. That was router 1. Now we go to router 2. Conf T, paste. See that? You see how it's building adjacencies? Awesome. Let's go to router 3. Config T. And there's the reality, ladies and gentlemen. I can tell you right now, everybody copies and pastes. So learn how to do that. Even on the CCIE exam, they allow you to do that. So as long as you know where to put it. I know that I was told one time back in the day, either know it or know where to get it. All right, so 4, router 4, or I did router 4, okay. Router 5, config T, and we're going to go ahead and paste that right there. Boo! And then last router, config T. Oh, not copy, paste. All right, and then should have done WR way up there, sure did. Let's go back to router 0. Let's maximize this big boy. And let's take a look at what we have. Show IP route. Boom. And we have right there all our networks that we're learning. We're learning about the 10.1.1.8, the 10.1.1.12, the 10.1.1.16, the 10.1.1.20, the 10.1.1.24. All right, you can see the administrative distance of EIGRP, which is 90, and the metric. But later in our course, we will be learning about, very important, show IP EIGRP topology. And we'll get into that once we get to that particular lab, what these numbers mean, and we'll learn how the actual protocol gets it. Okay? So that right there, ladies and gentlemen, is a basic configuration of RIP. And what I've always said, ooh, let me close this. Let's go to router 0. All right. Is this router 0? No, this is router 1. Let's go to router 1, 0. Oh, what happened? Oh, I must have closed 0. All right, router 1, doesn't matter. Router 1, all right. But what I've always said, here we are in router 1, which is this router right here. And I'm going to ping all the way over here. Okay, we're going to ping the 10.1.1.17, which is this side of that particular interface. And it got there. It got there. So we do have connectivity, and we can check each and every one, but we know we have connectivity across the network. Basic configuration of EIGRP. One command you cannot forget. All right, no auto summary. And I will explain this. I want you to remember that, what I just said. Don't forget no auto summary for disinfector routing protocols. And this is a disinfector, advanced disinfector, but it's a disinfector nonetheless. But I'll explain something later on in the course about wildcard masking. All right, I'm not going to get into it right now. So I'll see everybody outside the lab. All right. All right. Dude, that was fast. That was simple, quick. All right. All we had to do was advertise one network. You saw what happened with the RIP, that it went back to the class A, right? I put in 10.1.1.4. It goes to the 10.0.0.0. That happened in RIP. It would have happened here the same thing. So why do that? But then we even got quicker, didn't we? We said, we're going to go ahead and get not lazy. We're going to get efficient. We're going to use Notepad. We're going to put the configuration in Notepad, and then we're just going to copy paste all the way through. Now, some people in the real world are going to tell you, don't copy paste. That's not the way you learn. Okay, I can see that. But guess what? Everybody copy paste. They have their spreadsheets. They have their Notepad files with the configurations, because the only thing that really changes sometimes are bandwidth speeds, IP addresses, maybe the host names. Okay, that's it. But it's the same thing. It's the same configuration. So just have it on Notepad. Copy paste, copy paste, copy paste, copy paste. You saw how quick that was. But what I wanted to point out simply was that is the basic and that is the normal type of configuration that we used in the original CCNA. Okay, and I believe you will still do it that way. What you need to pay attention to that everything is on the same autonomous system. I can't stop that. And if you are going to configure it like we just did, all right, that you put that no auto summary. You will see when we configure with wildcard mask that won't be a necessity. All right, but if you're going to use the class full boundary of the address, then you must put in the no auto summary that tells it to send out the updates. Okay, when it sends out the update, to send out the summary mask. All right, but that's it. Very simple. A lot of routers, a little redundant. It gets redundant after a while, but everything was working just fine. Now we start getting to other things, but once we get there, we'll learn them. See you next. All right. What are we looking at here? It's the same lab that's in the background. What I did, I just opened up router 1, all right, because we did configure EIGRP, and I did the show EIGRP or show IP EIGRP topology, all right? And there are the codes, right? That you have your passive active, which is what we're going to talk about. You have update, query, reply, and reply status. All right? You can see that on the left-hand side, right by each network that the router has learned, there is a passive, and that is good. We want to see that. All right, we want to see that there are P's because that means it has converged. We know about that network. Now, where you say it has one successor, two successors. Whoa, look at that. So now we have something that we can go two different ways to the 16 network. So that means we have a feasible successor, right? That means, boom, hey, we can go either way. As you can see, you make the decision based on the lower metric. So this has a lower metric. Okay, so you can analyze by going back and forth in which direction. So we're on router 1, and it's via the 10.1.1.5. The 10115 is this interface right here to get to that particular network, which is the 16 network, okay? It will be the preferred route, all right? And the same thing goes over here with the 10120, whereas the 26844, or, well, here we go, the 217, whatever, okay? But you can see that the feasible distance will change, okay, throughout each particular network it goes to. And you can see how small this number is because it's via a connected interface. So the feasible distance will definitely be shorter because it's advertised from your neighbor router. All right, so this is the kind of things that you look at when you go into your topology table to see if you do have multiple paths that you can go to one particular network, okay? That will help you say, okay, what type of lines are there? Do I load balance? Do I tweak it and make it go this way instead of that way? So there's many things you can do, but definitely we do have feasible successors because there's two successors there. All right, and that's what the feasible distance is. It's pretty much just a little overview of it, telling you coming from the other router, hey, this is the best number to use. Okay, now that's what is being advertised anyway. All right, because you see the 2686976 is right here. And if you were to look, I earlier did show IP route, so I'm just going to scroll up, and this is for the 20 network. Okay, you can see that for the 20 network, you have the 268.976, which is the feasible distance. Okay, and that will be the successor route, and it made it there. Even though it's showing you that it's going both ways to the 10.1120, okay, and this is where you use both tables. You look at your topology table and you're analyzing and you're saying, okay, this is telling me it can go two different ways, like it's telling you right here, and this one's a fast Ethernet, okay, and this is a serial, so I will bargain it will use this, right? It will use, even though they're the same, because obviously this is a lab. Okay, I'm going to minimize this real quick. So we were on that router right here. We're trying to go to the 20 network, which is where? 28, 24, 20, right here. And we're sitting up here. So this is a slower way. That's why it has a higher number. Serial, fast Ethernet, and then it gets to the router. Where here is fast Ethernet, serial, fast Ethernet. We're right here. Somewhat similar, that's why they have the same number, but we're going to change that later on when we start playing around with the interface and changing the bandwidth on certain routers, and you'll see how those numbers will then change. Okay, but let me just tap this right here, bring it back up. But this indeed is your topology table, and this is the things that you may see, but what most interests you is these two different codes. You know it's got to be passive, and taking a look at which, because it's going to be based really on that number, okay? If they give you a print screen, if to go to this network, which number will you choose? It's always the lowest metric. And remember, with RIP version 2, everything is based on hop count, where an EIGRP is based on the lowest metric. Lowest hop count for RIP, lowest metric for EIGRP, lowest cost for OSPF. All right? But there you go. But again, you just can't decide on your topology table. You look at it, you analyze it, you bring up your other table, and you say, here's my routing table. These are my successor routes. What is it telling me here? And you go back and forth, or you can do a side-by-side comparison. So you can analyze, because you, as a network engineer, need to understand what is actually being connected. Are these fiber lines? Are these T1s? Are simple Cat5? Or are we looking internally? What is it? How are they going across? Is it serial? And if it's serial, is it a wide area network? Are we running wide area network protocols? If we are, what is the speed of that wide area network? Okay, so all these different things. Is it a Metro E? All these things come into play when you're looking at things and saying, okay, which way do I want them to go? And then you can tweak or load balance using the variance command, however you think you should apply it based on the needs of your design and your network. See you in the next. All right, welcome back, everybody. We've been talking about EIGRP, the routing protocol. Obviously, everything that it does is features. We've looked at we've configured basically or basic configurations of EIGRP, and we've looked at the topology table and even looked at the routing table. So one of the things that I pointed out in the topology table was the feasible distance and how it's going to calculate the metrics. All right. So this is one of the things that we're going to talk about now. Oh, I forgot I did that. Okay. So we need to know a couple terms. Now, I'm not going to kill you all these terms, but you do need to know. I'll tell you which ones you actually do need to know because you may be asked in a question. Okay. The first is the reported or advertised distance. Now I'm going to back this up in the next slide with a little drawing that I did. Okay. And then we're going to go right into I'll go into our lab, which I kind of changed a little bit, and we'll see how that works. I'll show you the topology table and where these numbers are at. But the reported or advertised distance. Now, this is the metric that's being advertised by your neighbor. So your neighbor is advertising to you, hey, to get to this network, this is how much it's going to cost you. That's the little metric right there, okay? And it's also is the second number in the topology table. All right, so in the topology table, you have your parentheses, and there's two numbers. The second number is that advertised distance from your neighbor. The feasible distance, this is important, is the best metric all paths to a remote network. So the lowest feasible distance is the one that makes it to the routing table, okay? And that's what it says right here. Lowest FD makes it to a routing table. So that's important. So when you're looking at the topology table, you see the feasible distance. That is the one that it calculated. And how does it calculate? We're going to learn that in a second. All right, that's the one that it tells you, hey, this is the way we're going to go, and that's why it makes it to the routing table. All right, now the neighbor table, and we talked about that as well, it's information about your neighbors. What does it tell you? Well, it tells you the IP address of your neighbor. It tells you how long it's going to hold that information, the smooth round trip timer, and the queue. And remember, as far as what you need to know about your neighbor, yeah, okay, the IP address, the whole time it is important. It's a default 5 seconds. Or the hellos are because it maintains that neighbor relationship with your neighbor every 5 seconds. And the reason that it doesn't need to be the same is because it doesn't need to tell all the routers. It's just going to make them aware, hey, this was going on. So that's why your hellos don't need to be the same. All right, but that's why you got the hold down timers that you can actually tweak and can hold the information longer, because that tells the router the hold down timer. And that's one of the things that you may get asked. All right, was the hold down timer, what happens when it expires? Well, then it tells your routers, your neighboring routers, hey, to get to this particular network, yeah, it's dead. It doesn't exist anymore. All right, so that's what that's for. Now, the topology table is populated by the neighbor table and obviously using the dual algorithm when it calculates this metric. All right, so it's a combination of both, and we know already that it holds all the routes to the entire remote. All the remote networks are there, and the successor route that's in the topology table gets copied into the routing table. All right, the feasible successor, that's the guy who came in second place. Now, I want to read this verbatim. Path whose advertised distance, because this could be a question, I don't know. Path whose advertised distance is less than the feasible distance of the current successor and considered a backup route. EIGRP can keep up to 32 feasible successors and probably more, okay? And probably more. It can hold a lot more now with the newer iOSs, but hey, 32 feasible successors, I think that's quite a bit, all right? But what you need to pay attention is this first sentence. Path whose advertised distance is less than the feasible distance of the current successor, okay? Who's lower, okay? Or the current is advertised distance less than the feasible distance of the current successor. So that's the guy basically in second place. That's the one that's going to stay in the topology table. That is the backup route in case the successor route, which is the best route to the network, okay, to the remote networks, makes it to a routing table. It's the backup for that. So if the successor route fails, remember I said this already, when we looked at the topology table, it will query it, and hopefully you'll have a feasible successor that can grab that information from. Okay, so we have this terminology and this information will be available to you. All right, so you don't have to, oh my God, he's in the way, I can't see. It's going to be there for you, so you'll be able to look at it, download it, what have you. But we need to know is how do these numbers come about? Okay, and basically, I mean, I drew this just so you know it's a network and this is a remote network over here. But you have 3 routers. Okay, and you can see I put it here. Okay, the advertised distance, meaning this neighbor is advertising to get to this remote network. Okay, it takes it 1,000. So it's telling, hey, you want to get to this network, it's going to cost you 1,000. All right. And to get to this network in Florida, right, or through Florida, is going to cost you 1,500. So this guy over here is saying, I want to get to that network, but which way do I go? So what is it that I do? Okay, very simple. Okay, you're going to come here. If I can, there you go. Get the pen out. So you're going to say, okay, if I go through California, what happens? Well, I'm going to take that 1,000 that my neighbor is advertising to me. That is the advertised distance, not the administrative distance, but the advertised distance, plus my metric to get to California, which is 500. Right? I add, that is a plus symbol. I add those two, I get 1,500. So that means the feasible distance, right? That gives me a feasible distance to get to that network right there. So through here, if I go through California to get over here, that's going to cost me 1,500. Okay, not a problem. Now we know. All right, now let's do Florida. Let's calculate Florida. No problem. Florida is 1,500 to begin with. That's the advertised distance right there. So Florida, 1,500 is the advertised distance, right? That's what Florida is saying. Hey, you want to get over here, it's going to cost you 1,500. And for me, it's the same, 500. So if I add those two, let me see if I can make a better plus so you guys don't laugh at me. There you go. All right. It's going to be 2,000. Well, it's going to cost me more to get to this network if I go down this way. So then that feasible distance over here is bigger than California, because California was 1,500. So it's going to choose based on the feasible distance, which is the best path to the network, the remote network, which you just went over the terminology. So I'm going to go the other way. But since we have 2 paths, this could be a feasible successor. Okay, could be a feasible successor. All right, but we'll see this now in the lab. So this is how the math works. No big deal, right? The advertised distance from your neighbor plus your own metric, okay? You add those two, you get the feasible distance. That's all it is. And if we look at it here, let me escape out of here. All right, and let's bring up router 1. And you can see I added a network here. This is the 2.0 network. I already added it to router EIGRP 130, so it's being advertised. All right, and the same here. So we go to router 1, and let's maximize it. And let's do enable, and let's do a show IP EIGRP topology. Okay, boom, 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 boom. Let's get it all out there. All right, so we do the EIGRP topology, and the 200 network, or the 2 network, I should say, the 2 network, if you look at it down here, you see the feasible distance is that number right there, 217.4976. Now, I know you're supposed to say it's the lower metric. It's the lower metric. But this is the feasible distance. That guy right there. And it's this one, 217.4976. All right, but why is that? You should say, well, man, shouldn't I choose this? Because let's take a look at our routing table. Let's make a comparison. See who will be the successor route. to the 2 network. And see, and it chooses, you got 2 ways to get there, right? Through the 10, which is the fast Ethernet, or through the 10115. Now it's like, well, what? But look at the feasible distance number. That 37160 that we saw in the topology table, okay, if we scroll down, that 30720 that we saw, it's not going to come into play. It's not going to come into play at all because the feasible distance is this number that we're looking at as the feasible distance that is the best path. Well, Laz, how can that be the best path if the other number is lower? Well, let's take a look to see exactly which way it's going to go. Or not from there, sorry. Let's do this again. Come here. From here, we want to go here. And let's go ahead and auto capture play. And it's choosing to go to the 10, down to the serial, and then that way. So that's the way it's choosing to go. And that's the way that we looked at it when we saw it in the routing table. All right. That was going to choose via the 10 network right here. Yeah. All right. Because of the feasible distance. So based on these numbers, based on these metrics, the key thing to look at when you're looking at the topology table is the feasible distance, because the feasible distance, by its definition, is the best path to the network. Always keep that in mind. All right. Now you know the math. Now you know how to figure it out. It's just a matter of practice, practice, practice. Now also keep this in mind. You don't want to have too many feasible distance or many feasible successors, I should say, because if you have too many feasible successors, it could be, and again, this is out of the scope of the CCNA, you could run into a routing loop issue. But again, it's beyond the scope. You should have at least, like the number states, up to 32 feasible successors. Have 1, 2, or 3 backup paths that if one fails, the other one can just query its own topology table and put it in there so you won't lose communications. I'll see you in the next one. All right, welcome back, everyone. Remember, we're talking about the neighbor table. Very important, the neighbor table, okay? So we're going to go inside the lab now, and we're going to take a look at, we're going to do the show IP EIGRP neighbors, and we'll see what the neighbor table looks like. Obviously, it's going to show us information about our neighbors. I'll see you inside. All right, so we learned a little bit about terminology. Now we're going to take a look at the neighbor table, which we know helps populate the topology table. So let's go again back to router 1, and let's take a look, and let's maximize it, and let's take a look at our neighbor table. All right, neighbor, show IP EIGRP, EIGRP, neighbor. Oops, spelled it wrong, and there we go, neighbor. So you can see right there, it's giving you who are your neighbors. And let's take a look at this. Let's do a little side-by-side comparison here. All right, let's bring this all the way over here. Here we go. And let's bring this down. It says here, all right, that the 10.1.1.10, which is this interface right here, that's our neighbors. All right, that is our neighbor. And that is our neighbor's interface right there, the F00. Now we go to the hold time in seconds. All right. Now the hold time in seconds, that means, well, or we have the hold, because we haven't all the way. Let's maximize this, because there we go. There you go. Now we can understand it a little bit better. So we have there the hold time and the up time. Now you can see it's been up for 2 minutes, 48 seconds. The other one's been up for 2 minutes, 39 seconds. It's going to hold for so many seconds, and again, that means how long it's going to hold on the information before it dies. And it's going to die if it doesn't get any hello updates, because remember, EIGRP bases its adjacencies with its neighbors on those hello timers. All right, and those hello timers by default are set to 5 seconds. Every 5 seconds, I'm getting an update, an update, an update. It's going to hold it for such a long period of time. We also have our smooth round trip timers. okay, which is really beyond the scope of the certification. All right. Then we have our RTO and our queue count and sequence numbers. And again, really all you really need to be concerned with is, hey, this is my neighbor and this is my hold times and how long, not really how long I've been up, but who your neighbor is and the interface. All right. That's what your neighbor table is, and that it helps populate your topology table. That is it. That is it. And we see it here when we did that side-by-side comparison that this indeed is our neighbor, the 10115, or the 10115, which is this particular interface right here, and the 10110. So we're getting information through the serial 001 and the F00. That's the information that we're getting, where we're getting it from this particular routers, which is our neighbors. That's why it's called the neighbor table. All right. I'll see you outside the lab. All right, that wasn't so bad. It's simple stuff. It shows you your directly connected neighbors, the interfaces that you're learning it on, and obviously the IP addresses, all right, of your neighbors the whole time, the queue count, all that stuff. But just the fact that, just know that the neighbor table shows you your neighbors, okay? And that the neighbor table and the dual, we talked about this already, the dual algorithm will help populate the topology table, which is very important. See you in the next. All right, welcome back, everyone. We've already done a couple things with EIGRP. We've done basic configurations with EIGRP, but now we're going to configure EIGRP using wildcard masks, okay? Using wildcard masks. And again, I caution here that when you take your certification, all right, you make sure you read carefully what they're asking you to do, because if you need to troubleshoot a scenario, an actual simulation, all right, how are you going to do it? Do they want just the basic configuration like we did earlier with the no auto summary, or do they want you to use now the wildcard masking? So you have two things, two ways, I should say, that you can configure EIGRP. So be very careful. And I'm going to reiterate this when we come outside of the lab again, because I need to drill that in your head. Because before, in the 200-120 and earlier, that wasn't the case. It was the basic configuration, class full address, no auto summary, you were done. The networks, the no auto summary, you were done. Now we can use wildcard masking. So pay attention when you read in your certifications for your simulations, if you get one with EIGRP. I'll see you inside the lab. All right, here we are again in our wonderful lab. I took out EIGRP 120. So again, we have no routing protocol, no static routes. So we don't have connectivity going across the network. So what we're going to do now is configure EIGRP using wildcard mask. That way, we don't need to use the no auto summary command, because we're being specific as to what interface, what network we're putting that particular process in. All right, so let's go here. We're in router 0. Let's do a config T. Router, EIGRP, let's say 130, just to make it different. And then we say network or net. And this time we'll actually go 10.1.1.4, 0.00.3. That allows us, EIGRP allows us to do that. But I'll say something about that later. Net, let's just use net. We're using the 10.1.1.28, 10.1.1.28, 0.0.0.3. And then we're also doing the 32, net, 10.1.1.32, 0.0.0.3. Enter. I'm not putting the no auto summary there because I use wildcard mask, and I want to show you something. You saw that I copied, and I'm going to do a show start. I'm going to go all the way to where the routing protocol is, and you can see that it did not summarize. It did not summarize. I actually put the actual networks that it is advertising are there. That's the difference. But I'm going to tell you the pitfall of that. Okay, so you really got to pay attention in your certification simulation what they're asking you, or what question is that they're asking. So let's do router number 1, config T, router, EIGRP, 130, and you see we're still in a single autonomous system network, 10.1.1.8.0.0.0.3, and then I'm going to up arrow. I'm just going to get rid of the 8 and put a 4. And the reason I did it, because of that convergence is so quick, I don't want my typing to be interrupted. All right, I'm just going to do WR, which you cannot do in your certification, and I know I keep repeating that, but I want to make sure it's embedded in your brain. Config T, router, EIGRP 130, net 10.1.1.12.0.0.0.3, enter, and then up arrow, and then we do the 8. All right, do WR, that's going to copy that. We're in router 2, 0.1.2, then we go to router 3. Config T, router, EIGRP 130, network, what are we doing? Oh yeah, 10.1.1.16, 0.0.0.3, and then network, 10.1.1.12. Those are the two. Oh, and well, for the wildcard mask, and we're also using the fast Ethernet. So we're going to do network, and that's 32. So let's get rid of that 1. Boom. All right. Do WR. All right. Let's go to router 4. Config T. Network. 10.1.1.20. 0.0.0.3. Well, how about doing router EIGRP first, Laz? 130. Net 10.1.1.20, 0.0.0.3, and then the 16, 10.1.1.16, 0.0.0.3. All right, do WR. Let's go to router 5, and we got conf T, router EIGRP 130, net 10.1.1.24, 0.0.3, net 10.1.1.20, 0.0.0.3. All right, do WR. Let's go to router 6, conf T or conf T. All right, there we go. Router EIGRP 130, single autonomous system. Network 10.1.1.28, 0.0.0.3, which I'll probably get an update because I already have that one on top done. I'm just going to up arrow and put the 24 there. Do WR, Control Z. Let's do a show IP route from here. Show IP route, and let's maximize this so we can see what we're looking at. And we are getting from the 4, the 8, the 12, the 16, the 20, the 24, no, not the 24, the 20, and the 32, because 24 and 28 are directly connected routes. So we are routing. Let's go ahead and ping. Let's see, we got 4. Let's do the 8, which is up on top. Ping 10.1.1.10, right? .9. So we do have connectivity, but this is using wildcard mask. But I'm going to explain something outside the lab that you need to be careful with when using these wildcard masks. I'll see you outside the lab. All right. That was very simple. We didn't have to do the no auto summary command. Since we're putting the wildcard mask, it actually is telling you, hey, it's coming from this interface. The interface has a subnet mask. The updates are going to go out. The mask is going to go out on the updates. All right. So using the wildcard mask will allow you to, be able to network properly without having to use no auto summary. No auto summary. We don't have to use that. Okay. But again, I caution you. Read carefully for your scenarios. See the configurations that exist already. All right. You do have 10 minutes per simulation. So make sure that you're going to do the right configuration. Just the basic, EIGRP, the autonomous system number, network so-so, the class 2 boundary, not a summary, or the way that we just did it here using wildcard masking. Very important to read, understand what they want you to do. I'll see you in the next. All right, welcome back. We're going to go ahead and tweak it, right? We're going to go ahead and manipulate which way the traffic is going to flow. Now we're going to go ahead and go on this router. All right, we're going to tell it we don't want it going this way. We want it going this way. So we're going to manipulate the bandwidth on the serial 000 interface and on the F00 interface so we can make it go how we want it to go. And we're going to verify that by looking at our routing table, by looking at our topology table, and by actually doing the tracer command within our PC. I'll see you inside the lab. All right, we're inside our lab. And what we're going to do now is we're going to manipulate which way the traffic is going to flow. Now, by simply looking from PC1 to PC2, obviously is what I'm talking about. Just by looking at it, we know that we're going to go straight across because this would be the fastest way to get across, would be the fast Ethernet. All right, if we take a look at this router 0 right here and we maximize it and we do the CLI, what's going to happen is we're going to do show, well, let's do enable, and we'll do a show IP route. All right, and it's going to show us that, hey, we're going to go to the 2.0 network through the 10.1.34, okay? That's straight across a fast Ethernet 0. So we're going to go this way, all right? So we're going to change that. We're going to turn these interface, we want it to go this way. We want that packet to go this way. And you can also do a trace route if you wanted to. You go to the desktop, we go here, or trace cert, I should say, being in Windows, a trace cert, and we'll go to the 192.168.2.1, and we hit enter, and you can see you went to your gateway, you went to the 10.134, and then you actually went to the 2.1. So let's go ahead, and we're going to make it go up this way and across to get to its destination. Not something you want to do, but you can do it by tweaking just the bandwidth. So we're going to make this a very a slower bandwidth, and we'll make this a higher bandwidth. All right, and we'll just maintain what we have here. We do this by going inside the interface. So let's go to the serial 0. Let's go back to router 0. Let's open that up, and let's go config. Oops. Let's go to config T. Okay, that closed on me. Let's open that again. Okay. All right. Hit enter. Thank you very much. Interface S0/0/0. Now we're inside that interface. All right. And if you were to look at the original bandwidth, you can do a do show interface S0/0/0/0. If you can take a look at the original bandwidth was 1.544 kilobits per second. That if you were to look at the show interface F0/0, you see that the bandwidth, or do show interface F0/0, you will see that its bandwidth, let's see where it's at right here, it's 100,000. All right, it's 100,000. So we're going to slow that down, and we're going to speed the other one up. All right, we'll put it to its maximum. All right, so we're inside the serial 000 right now. So we're going to do bandwidth, and then you can see that the most you can do right there is 10 million. So that's exactly what we're going to do. 10, 1, 2, 3, 4, 5, 6, and that is 10 million. All right, you see the neighbors are changing, and now we're going to go into the interface. Let's see if I can just backspace out of here, make life easy. And we're going to slow down that bandwidth, and let's change it to 64. will make it really slow, do WR. All right, so making that change, if we were to look at the routing table, show IP route, what's this going to say now? Now you see that to get to the 2-dot network, it's no longer through the fast Ethernet, it's through the serial 000. You're going to the 10116. And you can take a look at the feasible distance right here. And again, a lot of ways you can verify. Show IP, EIGRP, topology, right? And it's going to show you. Now look how interesting this is. Now we got 3 ways, which is actually what we want to do, right? We got 3 ways that we can go. The feasible distance is 268.6976, which is 268.6976 right here, which is going to take us through the serial 000. Okay? Because look at this one right now. We put it so low that look at that particular distance right there. That's pretty big. It's like, well, there's no way it's going to go through there. All right? So we'll go back to our desktop, even though we've confirmed already with the routing table. We've confirmed by looking at our topology table and the feasible distance that it's using. We're actually going to go to the PC, all right, and we're going to do another trace route to the same one. Let's maximize that, and let's see which way it's going to head. It goes to the gateway, it goes to the 10.1.1.6, then it goes to the 10.1.1.10, then it goes to the 10.1.1.34, and then finally to the 2.1. So it took a longer way of getting there, and for whatever reason that you want to do that, you would, but normally, obviously, if this is the faster route, the algorithm chose this one, you would actually do that. But you can see how you can tweak in EIGRP because its algorithm does pay attention to bandwidth and delay, and it will create a better path, a best selection of which way it needs to go. And we actually just proved it right here. I'll see you outside the lab. All right, that was pretty simple. All you got to do is go inside the interface, give it a faster bandwidth, as you saw, 10 million, right? We gave it the maximum bandwidth through the S0000, and we gave a 64 to the F00, 64 kilobits per second. That's pretty slow, all right? So automatically, you saw when we looked at the routing table that is going up this way. The topology table tells you the same thing. But now, since we made this, we changed the bandwidth. Now you see there's a lot more ways that you can go in the topology table. You see the topology table has more, 3 different successor routes, right? 3 successors. But the feasible distance is telling you to go this way. So now we actually then did the same tracer, and now you saw that it was going up to the 10.1.1.6 first. So we manipulated that. Obviously, you may not want it to go this way. You definitely want it to go through the faster one, but just to show you that you can do that. And in order for us to do that, we have to mess around with the bandwidth. Now you can also mess around with the delay if you want to change things for other reasons, but know that you can do this because EIGRP's algorithm, the dual algorithm, does pay attention to the bandwidth and delay, right, which are their K values, to make a best path decision. See you in the next. Alrighty, welcome back. We have learned on how to tweak our bandwidth so we can manipulate which way we want it to go. And we saw that it's just going this way. But you know what? We want to load balance. We want to load balance, and you can do this many ways. One of the ways that we're going to do it, or the way that we're going to learn, is using the variance command, which it uses a multiplier and multiplies it, whatever it is. It's 1 through 128. It will multiply whatever number you put there to the feasible distance to include other paths. Because we want to include not only this way, but we want to send it down also. All right, we want to send it down also because we went solo on this. There's not even going to take this into consideration, but you'll see when we get into the lab. So without further ado, here we go. All right, we're back in the same lab. Now you saw how we were able to manipulate which way our traffic was going to go by just changing the bandwidth on that particular interface. And you can also play around with the delay. You can change the delay as well. I mean, you can tweak it to whatever meets your needs, okay? But also we need to know how to load balance. If you remember in our router 0, when we changed the bandwidth, it gave us this to the 2-dot network. It gave us various ways to go. So let's say we want a load balance between these two interfaces right here. You see the feasible distance is this, which doesn't include this particular one. So I wanted to include at least these two serials. So there's a command within EIGRP, because if you look at the routing table, show IP route, there's only one way, which is through the 10116. We verified that last time. So I want to include both serial interfaces. So what we're going to do is, I'm going to say config T, I'm going to go router, if I can spell it correctly, there you go, router EIGRP 130. And I'm going to say variance, because the variance command, what it does, it uses a multiplier, which we're going to put in there, to include other not successor routes in its calculation. Variance 2 is going to take the feasible distance and multiply it by that number. Okay? And you can see you start making new adjacencies, do WR. And if we were to look at the routing table now, show IP route, okay. Now we're load balancing between both serial interfaces, and you can see that one feasible distance, it's lower, right? Or let's say 26895, all right, then the other, all right, so it's going to also choose that route as well, okay? Because we're dealing with the bandwidth, right? Even though this bandwidth is going gigabit speed, right? This one is only going 1.544 megabits per second, which is the default. By using the variance multiplier, I told it, hey, listen, let's send traffic across both of these interfaces. And sure enough, it did. It calculated it, recalculated it, and said, okay, let's include these two interfaces. We lowered so much the bandwidth on the fast Ethernet that's not even looking at that interface to even go through it and put it in the routing table. And that's what the variance command does. Now, if you want to get rid of it, it's very simple. Just go back to your EIGRP router, EIGRP 130, and just do no variance. All right, and then you'll get new adjacencies coming up again. Let's do a do WR, and let's do a show IP route. And there you go. We're back to what we were before. So it's not taking into consideration anything but that one that we changed the bandwidth on to 10 million, which we're going at gigabit speed. All right, there's your variance command. All you got to do is go inside EIGRP, type variance, choose a multiplier, so it'll include all the other interfaces you choose or you would like. And then, boom, you'll start load balancing across both interfaces. And that's it. I'll see you outside the lab. All right, that wasn't so bad. You saw that it was 3 ways that we can go. We used the variance command, and it actually included both serial interfaces in the routing table, where before it was only one way, which was going up. You saw how to take it out. Now, I did mention there was more than one way of doing that, which is using the maximum path cost. You can go ahead, or maximum paths, right? You can tell, only go, let's say, or go this way if it's 3 or what have you. You want to go the lowest paths. If it's straight across, whatever it is, you can use that as well, all right? But definitely load balancing should be part of your arsenal in your networking tools, I guess you want to call it, knowledge, because you do want to go ahead and send traffic more than just one way if it's big packets that you're sending, not to burden each, the bandwidth that you have on each interface, and just for the sake of the fact that, hey, you got things going different directions, okay? That's your variance command. Very simple to do. Be wise when using it. Take a look at those metrics. Very important. See you in the next one. All right, we've made it to the summary of this particular section. So we need to find out, what in the world have we talked about? All right, we talked about EIGRP concepts, everything that EIGRP deals with, the administrative distance, the algorithm. We've talked about the basic configurations, right? The autonomous systems that we use. And in the basic configurations, it was a classful boundary of the address that we used, and we had to use the no auto summary if you're going to do that. If you're going to use just the classful boundary addresses, you must put no auto summary in order to work. And remember that you have to use complete. You have to have the same autonomous system across the board for single autonomous system EIGRP. Topology table, we went into a little bit of depth in the topology table. All right, we took a look at what you need to know, like the active and passive. Those are very important. All right, and the feasible distance. But the feasible distance, we saw that that's how we get our successor routes and our feasible successor routes based on that calculation that we looked at of the advertised distance from our neighbor and what we're advertising to get to that particular neighbor. So it comes out with a feasible distance. All right. Also, it takes, because of dual, EIGRP uses those K values that must be the same, Because remember, EIGRP keeps adjacencies, all right, with the routers based on hellos, right? And they don't have to be the same. But the K values do have to be the same. So be very careful with that, because if your bandwidth or delay is different on one or the other, you may start running into different things. Remember, there's bandwidth, delay, reliability, load, and MTU is a throw up, right? Maximum transmission unit. It's not, they don't mention it as much in there. And if you will Google it or Wikipedia it, you'll see that there's a big discussion about MTU. Yes, we do use it. No, we don't use it. So it's up in the air. But those are your K values. And of course, you already said the successor and feasible routes. The neighbor table, important, tells you information about your neighbor, the interfaces, the IP addresses the whole time, right? The queue count, smooth round trip timer, queue, all that good stuff. But more importantly, the neighbor table and the dual algorithms are the one that populate your topology table, because your topology table holds all routes, all remote routes, okay? Connected and not connected. So it is important. And it also holds what? It holds the feasible successor, the one that stays there as a backup for the successor route. So you see how they all come together. Here you see where it says careful, 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 because in the older CCNA, which is, CCNA 120, they just changed it not a couple months ago, all right? It was the basic configuration for EIGRP that we used. Router, EIGRP, the number, network, classful boundary, network, classful boundary, whatever it is, and then no auto summary. That was the criteria. Now they're saying, hey, look, you can configure EIGRP using wildcard mask. That throws a flag up in there that when you do your simulation, please read carefully that they're not making a hint, or they're not hinting towards you configuring it using wildcard mask. Take a look, because if it's a simulation, more likely all your computers will be connected to routers. And if you can go inside and do a show run, take a look at the configurations they already have there for EIGRP and see what they have. So just mimic it, all right? If they have wildcard mask, use wildcard mask. If they do not, then don't. Use the basic configuration, all right? And also, we learned how to tweak our bandwidth. Going inside the interface, right? Changing the bandwidth, manipulating the where we want it to go. And I say you can also use the maximum paths also if you wanted to. And finally, we did load balancing using variance by using a multiplier, because it's basically just going inside the routing protocol. You saw it, and putting the command variance and then a number. The number could be 1 through 128, because you got to look at your metrics to see what metrics you want included. We wanted those two serial interfaces included, so we'll use a variance of 2, and it included that in there. And now we have things going across both interfaces. But that's it. That's your EIGRP. That doesn't mean that, hey, don't practice more. Definitely create different topologies, not just the one that you see here. Mimic the one that I have. Take away a link. Do just 3 straight routers going across. Make different types of topologies so you can see how EIGRP actually works and plays and goes crazy, change the bandwidths, all these different things you can do so you can understand. The more you play around, the more curious you are, you'll get better understanding of everything. Books are not going to teach you everything. It's experience. And how do you get experience? If you don't have the equipment, all you have is the simulators, that's fine. They mimic what they're supposed to mimic. All right, so go ahead in there and play, practice to your heart content. I'll see you guys in the next.